Okay, so what I want to do in this video is review these three right-hand rules and do some applications with these three right-hand rules. If you are watching this video, I hope that you have at your disposal this PowerPoint presentation, which you can find in the Chapter 20 materials up online, and also a loop that you can use. If you're doing this from home, you might not have the best loop in the world, like rolls of duct tape can work well, or wires that you hooked together to make a circle, or get creative. But you need a loop so that you can use that first right-hand rule. So before we do any demos, let's just review what these rules are for. So this first right-hand rule up here is for the magnetic field, which we abbreviate with a B, that's created by a current carrying wire. So to use this right-hand rule, you put your thumb in the direction of the current and the way that your fingers wrap. And remember, you start with your knuckle and you wrap to your fingertips. So imagine a vector that starts with your knuckle and goes toward your fingertips. The direction that your fingers are wrapping is the direction of the magnetic field. These next two right-hand rules are for forces on either a current carrying wire, which would be the second right-hand rule, or a charged particle that is moving with a velocity v for the third right-hand rule. A lot of times people have a hard time figuring out which right-hand rule to use, especially if we're talking about currents, because both of these two right-hand rules have both I and V in them. If the question is not asking about a force, chances are very good that you do not need to use the second right-hand rule. So there is no force with this first right-hand rule, so the question is not asking you about a force. I would go there first. I would also like to point out that these two right-hand rules both have B in them, but they are different B's. And here's what I mean by that. Up here on the top, the first right-hand rule, this is the magnetic field that is created by this current carrying wire. So if you have a problem that doesn't have a magnetic field and there's a wire there, you're going to want to use this one because this one can tell you what kind of a magnetic field is created. This second right-hand rule, this B here, is not the magnetic field that's created by the current carrying wire, but an external magnetic field. So a magnetic field that this current carrying wire exists in the presence of. So maybe there's a magnet nearby that is creating a magnetic field, that B. So if we had a magnet creating a magnetic field and then a current through a current carrying wire, then that current would feel a force. So I have a couple of video demos that we're going to do using these right-hand rules. So let's get started with this first one. So I have a strong magnet with the North Pole here and the South Pole down at the bottom. And you can see we always know that magnetic fields leave North Poles and enter South Poles. So we can think about the magnetic field starting from the N and traveling to the S. So there's a magnetic field that points down in this video. And then this yellow line here is a current carrying wire. And so if we have a current carrying wire in the presence of an external magnetic field, a magnetic field that it did not create on its own, then it will feel a force. Okay, so I want to just do a quick right-hand rule with this. So let me get it on the board and draw what's going on. So we had a magnetic field that we said pointed from that North Pole down to the South Pole. We know that magnetic field lines always point from N to S. And so that's what the B looks like that. That's what our fingers will do with this right-hand rule. And I also have a current carrying wire that does this. Let me get a different color. So the current in this current carrying wire is traveling to your right. So that's what I looks like. And we want to figure out how this is going to move. And so we're going to use that right-hand rule that is for forces, right? So here I have a magnetic field, not the magnetic field that is created by this wire, right? If this was my wire and it looked like this, the magnetic field that's created by this wire, I'd put my thumb pointing to the right, and now my fingers would curl out and up and down and in. And that would be the magnetic field created by that wire. Now that looks nothing like what I've drawn on the board, okay? So this is an external magnetic field that this current carrying wire is traveling through. So when a current travels through a magnetic field that it didn't create, that wire will feel a force. So we'll use the second right-hand rule to figure out what direction that force should be. So we put our hands in the direction of the B. By hand, I mean palm. So you want to imagine that there's a vector that starts at your wrist and moves out to your knuckles. And so it starts at my wrist and it moves out to my knuckles like that. So that's my down. And then I want, oh, I didn't do that well. Your palm in this rule, and if you have the PowerPoint up on the screen, is not B, but I. So I want my palm to go in the direction of I. So we'll go like that. And now I want to turn my fingers so that they point in the direction of B. So if I turn my fingers here, they do not point in the direction of B. So my fingers are pointing into the page, but I want them to point down. So I can turn my hand all of these directions, and my hand, my palm still points to your right. But if I go like that, now my palm points to your right, my fingers point down, and I see that my thumb points into the board. So our right-hand rule says the force should point into the board or into the page or something. So when we do this video, we should hopefully see that the wire will move into the board here, and we'll call into the board probably toward that man in the video. So let's watch and see if that's what happens. So we'll say in toward the narrator. All right, so congratulations, we were correct. Let's do one more example. So this is a different kind of example. So let me just get this video started and we'll stop it if we need to explain a little bit better. Okay, so what this tube is it's a cathode ray tube, and it's connected to a battery, but this is a very high voltage battery or power supply. So the positive terminal is coming out of this yellow end, and the negative terminal is going into the black end. And there's really mostly just air in here, but there's 5, maybe 10,000 volts across these two terminals of the battery. And so when there's power connected to these two ends here, it's going to ionize the air inside the tube. And that ionization of air releases electrons. So we have a current of electrons that are flowing through the air toward the right in this video. So from the yellow to the black. Okay, so let's draw this out. So, okay, so here's a video of this. So we said we have this tube, and it looks like that. And inside this tube, we have motion of electrons moving to your right through that tube. So we need to figure out what is going to happen to this beam of electrons as the south pole of a magnet is approached. So what he's going to do is he's going to bring the south pole of the magnet into the beam of electrons. And that is going to basically bring it, as I'm drawing it here, into the page. Okay, and now we know that magnetic field lines always point out of the north pole of the magnet and into the south pole of the magnet. So we want to use that, okay? So B field lines. So now would be a great time to pause the video and use this information to try to make sure a determination for yourself for how you think the magnetic field should point on this piece of paper. So if you've got it figured out, if you don't have it figured out, pause it and do it yourself. If you've already got it figured out, I'm going to say that the B points out of the page. Okay, so the south pole of the magnet points into the page. That would be an X here. But I know that magnetic fields are going to point into that south pole. So the magnetic field lines are pointing out of the page and into the south pole of the magnet as it approaches this page. Okay, so now we should use our right-hand rule again. So let's go back to the PowerPoint and figure out which right-hand rule to use and how to use it. So we're talking about V, we're talking about the motion of charged particles. So I'm going to come down here onto this bottom one here, where my palm is for V, my fingers will turn in the direction of B, and then the force will be my thumb. So taking my right hand, I'm going to make my palm be V. So that's this direction here, the arrow that points to the right. So there's my palm. I want to turn my fingers so that they point in the direction of B. And that's easy for me to do here. So I'm going to turn and have them point up toward the camera, up out of the screen. And now I see that my thumb points down when I do this. So I should get a force that points down. Okay, so this beam of charged particles is going to feel the force that points it down, which means that this beam of particles should be deflected down. So let's turn the video back on and see if that's what happens. Let's say it's deflected downward. And it is most certainly not deflected downward, it's deflected upward. So let's talk about what happened. Some of you might have noticed while we were doing it, but what happened is that this is a beam not of positively charged particles, but a beam of electrons. Okay, so when you have negatively charged particles, you do everything the same, except that you need to now remember that the force will point in the opposite direction. So that a beam of positively charged particles would have been deflected down, but for a positive charge. But FB points up for a negative charge. Okay. Let's go do this hard homework question. So I'll give you a moment to read that question. All right, so let's get both of these things up here on the screen. Don't see the one that I wanted. So just make this be here like that. Okay, so I have my horizontal wire carries a 24 amp current due north. Okay, so I have, I'll make north, this is homework question. North, east, south, and west. And I see that I have a current going in a wire going due north. So let's draw that. That's what I looks like. And I want to know what the net magnetic field is 20 centimeters due west of the wire. So I'll call this distance here is 20 centimeters. What is the magnetic field if the Earth's field there points downward 44 degrees below the horizontal and has that magnitude? So this is hard because we need to think hard about Earth's magnetic field. So let me pull up what's going on here. So this is a little graphic of what Earth's magnetic field looks like, and I'm actually going to draw this. I think I might have it drawn already somewhere there. Okay, I'll redraw it actually. So here's what Earth's magnetic field looks like. So we're tilted on an axis. So the North Pole of Earth is sort of not up here at the top, but off to a little bit. And actually, it's not a magnetic. Our North Pole is a magnetic South Pole, and our South Pole is a magnetic North Pole. So it looks like that. And we have magnetic field lines that point out of North Poles and into South Poles. So if I draw my lines, they should look like that. Out of the North Pole, into the South Pole. And let me get a couple more in here. Okay. So if you have a little guy standing at the equator, so here's what the equator is. The equator kind of looks like that. I'll make it look a little bit circular. So here's the center of the Earth. Let's put a dude standing right here. And to us as observers in the outside world, we think that he is standing sideways. But of course, he doesn't think that he's standing sideways because he feels the force of gravity, which pulls him in toward the center of the Earth. And so this direction here is up, and he's just standing normally. Okay, so if this guy has a compass, that's the line that is sort of horizontal flat surface that he stands on. And you can actually see how I've drawn these magnetic field lines. They're pretty much parallel to his flat. Okay, so Earth's magnetic field near the equator points pretty much due north. Let's come over here to a guy. I don't know, let's make her a girl. So a girl chilling up at a higher latitude. This is pretty much what happens here as well. We're at a high enough latitude to really feel this effect. So again, she thinks that she's standing straight up and down because the force of gravity is pulling her straight into the center of the Earth. So this is her up, and this is her flat ground. But if she is holding a compass, you see that Earth's magnetic field has a component that points north in the direction of the North Pole, but it also has a component that points straight down into the ground. And this angle here is the angle that Earth's magnetic field makes with the horizontal, is the dip angle. So this question is asking you about a dip angle. So let's come back to the question. So what it's saying is that Earth's magnetic field points downward. Now, it doesn't just point downward, it points north and downward. So on this diagram that I have drawn here, right, Earth's magnetic field points north a little bit, but it also points down, which as I've drawn it is into the page. Right? If this is north, east, south, and west, out of the page would be up, and into the page would be down. So it turns out that this is not the most useful way to draw this, because I'd like to be able to draw that 44-degree angle to be in the plane of the page. So let's do that a different way. So take this and flip it. Okay, so I would like to be able to resolve the direction north and up and down so that I can make sure that I'm resolving Earth's magnetic field. So let's redraw this, only now let's make north and south can stay here, but let's make up and down be in this angle. So actually, that's kind of hard for me to look at. I'm going to draw it a little differently. Let's make this be up and this be down. I like that better because up is up and down is down. And then I can make north be this way and south be that way. You can do it either way, but I find this to be an easier way to look at. Okay, so at this point here where the dot is, we have a component of Earth's magnetic field that points down and north with a 44-degree angle. And this here is the Earth. Okay, so this is a vector addition problem. And we have two magnetic fields that are impacting what's going on here at the location of the dot. We just resolved what the Earth's magnetic field looks like. We also need to resolve what the magnetic field is at this location due to the presence of this wire that's carrying current to the north. So let's think about that. So we want to figure out the direction of a magnetic field created by a current carrying wire. We have two right-hand rules that use I. And I'm hoping that you'll see here that this first one is the right one to use. Okay, so we want to figure out what is the magnetic field created by this current carrying wire. We don't want to figure out how this current carrying wire will experience a force due to an external magnetic field. That's not the question. So let's go back over here and try to figure that out. So we're going to use this first right-hand rule before I leave this. First right-hand rule, our thumb is going to point in the direction of the current, and our fingers will wrap in the direction of the magnetic field. So I'm going to look at this thing here, and I'm going to put my thumb in the direction of the current. So the current is going to the north, and now my fingers are wrapping in the direction of the magnetic field. So if I imagine starting at my knuckles and moving to my fingertips, I see that Earth's magnetic field is coming up and out of the page, and then to the right, and then down and into the page like that. So we are at this point where we are interested in, think about how Earth's magnetic field must point. If you don't know, pause it and think about it for a second. So Earth's magnetic field here points out of the page. So I have a little, and I said Earth's magnetic field, excuse me. This is not Earth's magnetic field. This is the magnetic field created by the wire. Everywhere over here is out of the page, and everywhere over here is into the page, like that. Okay, so the magnetic field is coming out of the page, to the right, and then into the page as it goes through there. Okay, so this direction here is not north, east, south, or west, but up. Okay, so at the location of the dot, which is 20 centimeters away from the wire, the location that we're interested in, we have Earth's magnetic field that points like this, and we have the wire's magnetic field that points up. In this drawing here, up is out of the page. In this drawing here, up is up toward the top of the page. So I don't want to do this whole problem for you, but I did want you to get set up with this. There's a couple of problems that ask you to look at this. So if the question is asking about a dip angle, you want to make sure that you are resolving up, down, north, and south in your diagram, okay? If the problem specifically says that there is no dip angle, so this would be that Earth's magnetic field points due north, probably it's for a dude sitting at the equator, then you can go ahead and draw your diagram with the northeast, south, and west cardinal directions. But if it talks about a dip angle, then you draw it this way, okay? So to show you where we are with that, right, so we had a 24 amp current due north, okay? So the magnitude of this is the magnetic field of a wire 20 centimeters away from a 24 amp current. There's an equation for that. You can calculate that. So you can get a number for exactly what this magnetic field is. Earth's magnetic field is 5 times 10 to the negative 5th Tesla. So 5 times 10 to the negative 5th Tesla is what you will label for the Earth's magnetic field. And now if I come over here, I've labeled these things. You need to calculate this number. You already know this number. And the total magnetic field at this point is the vector sum of this vector that points up and this vector that points north and down. So hopefully that will be a strong hint for solving this problem. Okay, so that is the end of the review that I wanted to do. And the next video will finish off a few pointers about chapter 20 on magnetism.